A metal component is spinning thousands of times per minute, pulled outward by enormous centrifugal force, and surrounded by gas reaching between 1300 and 1600 degrees Celsius. At temperatures like these, ordinary metal would rapidly weaken, deform, and eventually fail. Yet this component continues operating through thousands of flights. It is the first high-pressure turbine blade inside a jet engine, and its survival does not depend on an indestructible metal. The real secret is an entire thermal management system hidden inside a blade small enough to hold in your hand. To understand the danger, follow the air through the engine. The large fan at the front pulls in a massive volume of air. Most of it flows around the engine core to create thrust, while the rest enters a series of compressor stages. Each stage squeezes the air into a smaller space, steadily increasing its pressure and temperature. The compressed air then enters the combustion chamber, where it mixes with fuel and burns. The expanding gas rushes toward the rear, but before leaving the engine, it must pass through the turbine. The turbine extracts energy from this flow and uses it to drive the compressor and the front fan through a central shaft. The first high-pressure turbine stage receives the hottest gas in the entire engine. Its blades must rotate at extreme speed while remaining precisely shaped and perfectly balanced. Even a small amount of distortion could disturb the airflow, reduce efficiency, or cause catastrophic damage. So why do these metal blades not melt? The first secret begins inside the compressor. Before all the compressed air reaches the combustion chamber, a carefully controlled portion is diverted into a separate cooling system. This air is already hot from compression, but it is still far cooler than the gas leaving the combustor. The cooling air travels through passages in the engine shaft and enters each turbine blade through its root. From the outside, the blade appears solid. Inside, however, contains a complex hollow network that resembles a miniature maze. Air moves through serpentine channels that repeatedly change direction as they climb through the blade. Small ribs and turbulators disturb the flow, producing controlled turbulence that increases contact with the internal walls. In the most heavily heated areas, narrow jets strike the inner surface directly, removing heat before it can spread deeper into the metal. But internal cooling alone is not enough. The outer surface is still exposed to the high-temperature gas rushing past it. That is why the cooling air does not remain inside the blade. It escapes through rows of microscopic holes drilled at carefully calculated positions and angles. As the air leaves these openings, it bends along the blade surface and forms a thin protective layer between the metal and the combustion gas. This process is known as film cooling. Instead of allowing the hot gas to strike the blade directly, the cooler air pushes it slightly away and reduces the amount of heat entering the metal. The blade is effectively wrapping itself in a continuously renewed blanket of air. But this solution creates another engineering problem. Every kilogram of cooling air has already consumed energy inside the compressor. Air diverted for cooling cannot contribute fully to combustion and thrust. Using more cooling air may protect the turbine, but it can also reduce the efficiency of the entire engine. Engineers must therefore achieve the greatest possible cooling effect with the smallest possible airflow. That requires more than hollow channels and microscopic holes. The blade itself must also be made from an extraordinary material. Modern high-pressure turbine blades are commonly produced from nickel-based superalloys. These alloys retain much of their strength at temperatures that would severely weaken ordinary steel. They also resist oxidation and creep, the slow permanent deformation caused by sustained heat and mechanical stress. But their chemical composition is only part of the solution. Conventional metal is made from many microscopic crystals. The boundaries between those crystals can become weak points. Under repeated heating, cooling, and centrifugal loading, cracks may begin along these boundaries and slowly grow. To remove this weakness, advanced turbine blades are cast as a single crystal. During manufacturing, molten superalloy is cooled under carefully controlled conditions. Unwanted crystals are gradually eliminated until one continuous crystal structure grows through the entire blade. Without grain boundaries, the material becomes far more resistant to high temperature creep and cracking. But even a single crystal blade still cannot survive the turbine environment without another protective layer. The outside of the blade is covered by a thermal barrier coating system. A metallic bond coat helps protect the underlying alloy from oxidation. Above it, an extremely thin oxide layer forms a stable interface. The outer surface is then covered with a porous ceramic coating, commonly based on zirconia. Ceramic transfers heat much more slowly than metal. Although this coating is only a fraction of a millimeter thick, it can create a significant temperature difference between the hot outer surface and the superalloy beneath it. Tiny pores and controlled vertical cracks allow the ceramic layer to expand and contract without immediately breaking apart. The turbine blade is now protected by three mechanisms working together: cooling air moving through its internal passages, a film of air shielding its exterior, and a ceramic coating slowing the movement of heat into the metal. Creating such a blade is a major manufacturing challenge. The internal cooling network is too complicated to machine after the blade has been completed. Instead, manufacturers first produce a fragile ceramic core shaped exactly like the future air passages. This core is positioned inside a precision mold, and molten superalloy is cast around it. Once the metal has solidified, the ceramic core is chemically removed. What remains is a hollow blade containing a network of channels hidden deep inside its walls. The film cooling holes are then created using highly controlled laser drilling or other precision processes. Their diameter, angle, spacing, and position must be extremely accurate. If a hole points in the wrong direction, the cooling air may lift away from the surface instead of forming a stable protective film. That small error can expose a dangerous hot spot. Additive manufacturing is beginning to offer even more design freedom. It can create cooling passages and internal structures that would be extremely difficult to produce with conventional casting. But no manufacturing method can make a turbine blade completely invulnerable. Dust and sand entering the engine can soften or melt in the hot section, then stick to the blade. These deposits may damage the ceramic coating or block the tiny cooling holes. Without the protective airflow, the temperature of a small region can rise rapidly. Repeated heating and cooling also create thermal fatigue. The ceramic coating may crack and eventually separate from the surface. At the same time, the superalloy can slowly stretch under centrifugal force through creep. Even a tiny change in blade shape can affect clearances, balance, and turbine airflow. For this reason, turbine blades are inspected throughout their service life. Flexible borescopes allow technicians to examine the hot section without completely disassembling the engine. X-ray and other non-destructive methods can reveal hidden cracks, blocked passages, coating loss, or internal defects before they develop into serious failures. But if high temperature creates so many problems, why do engineers continue pushing engines to operate even hotter? Because higher turbine temperature can allow an engine to extract more useful energy from the fuel. Combined with high compression and efficient aerodynamics, it can produce greater thrust while reducing fuel consumption. Every improvement in superalloys, coatings, cooling passages, and manufacturing allows the engine to move closer to that goal. A turbine blade therefore survives, not because one miraculous material can resist unlimited heat. It survives because engineers prevent the full heat load from reaching the metal at once. They control every stream of cooling air, every material layer, every microscopic opening, and every fraction of a millimeter. From the outside, it looks like a small curved piece of metal. Inside, it is a miniature cooling system, a single crystal structure, a ceramic heat shield, and one of the most precisely engineered components on an aircraft. The turbine blade does not defeat extreme heat simply by enduring it. It survives by controlling exactly where that heat is allowed to go.